Hello, and welcome to TI Precision Labs. In this session, we will specifically discuss bootstraps and TI Ethernet PHYs in the following topics: how bootstraps work, why bootstraps are used to configure PHYs, and bootstrap types implemented in TI PHYs. For a refresher on how TI Ethernet devices work, please view the previous Precision Labs videos in the Ethernet series. Hardware bootstraps are a mechanism of configuring integrated circuits through hardware rather than or in conjunction with firmware. Critical functions that can either affect form or function of the PHY, such as MAC interface, auto-negotiation, and data rate, are often offered as bootstrap configurable to prevent unknown device states or damage to the device. Here you see an example strap configuration to set a TI PHY in RMII master mode. The different bootstrap configurations and operating modes will be discussed in more detail throughout this video. In TI Ethernet PHYs, bootstraps are 2-level or 4-level. Shown here is an example of a 2-level bootstrap circuit. Inside the Ethernet PHY is either an internal pull-up or pull-down resistor and a comparator. Strap pins are generally output pins. However, the GPIO acts as an input on power-up and reset, during which time the switch to the internal buffer is open, the switch to the comparator is closed, and the potential on the strap pin is sampled by the comparator. This potential value will determine what mode the device will be set to. Once the device has been successfully powered up and the strap has been set, the switch to the comparator opens, the switch to the buffer closes, and the GPIO behaves as an output. In TI Ethernet PHYs, strap settings can be overwritten through register writes, but upon hardware reset, the PHY will default back to the strap settings. In 2-level straps, the pin is either pulled high to VDDIO or low to ground. The large potential range between levels prevents noise, voltage swing, or other factors from causing an incorrect operating mode to be read, giving you peace of mind that the PHY will operate in the correct mode. Strap circuit information specific to each TI PHY can be found in the programming section of the device's datasheet. The 2-level strap resistor ratio table tells you what resistors to use for each operating mode. The ratio of the resistors R high and R low can be modified as instructed by the datasheet to configure the PHY by changing the potential on the pin. Here are some examples of strap tables that may be shown in a TI Ethernet PHY datasheet. These tables show what functions are affected by setting a strap to a specific mode. As an example, the AutoNeg strap table shows that the default setting for the RX error pin is mode 0, enabling the AutoMDIX function. To disable AutoMDIX, this pin needs to be strapped using the resistor configuration defined for mode 1. The target voltage columns describe the voltage level required on the strap pin to set the device in each mode, using VDDIO as a reference. VDDIO is used as the supply voltage for the comparators within the PHY, so we compare our target voltages to this value to account for any variation in supply voltage. As opposed to 2-level straps, 4-level straps have intermediate voltage levels. This allows for more functionality, being able to set 2 features with a single pin, but requires stricter component selection. There is a tighter requirement for resistor tolerance, leakage current, and other factors that affect component performance. The voltage thresholds for each strap level will be provided in the datasheet as shown by this example. Note that when using 4-level strap pins with pin sharing, the internal pulls of the connected device must be considered. Macs sometimes have internal pulls which will affect the strap voltage, and the external strap resistors will need to be adjusted accordingly. All resistors should use the recommended values with a 1% tolerance. Remember that strap voltage is sampled on power-up and reset. As a sanity check, you can measure the strap voltage while holding the device in reset to confirm the PHY will be set in the desired operating mode. While setting bootstraps for different modes, the functionality of the pins may change, which in turn will require a hardware design change. Note the difference in strap configurations and functional modes between a TI PHY in MII mode and RMII master mode. In RMII master mode, the PHY supplies a 50 MHz clock to the MAC through pin RxD3. This is not the case in MII mode. The RxD3 pin is an input to the MAC, and you will need to adjust your design accordingly when switching between modes. As an example of setting a 4-level strap pin, let's say we want to set a TI PHY to RMII master mode in test mode 4, using the example strap tables shown. From the 4-level bootstraps table, we see that the pins RxD0, RxD1, and RxD2 correspond to 2 bits each, a MAC bit and a test bit. Looking at the MAC interface selection table, RMII master mode corresponds to the MAC bit sequence 110. Now looking at the test mode table, test mode 4 corresponds to the test bit sequence 001. To set MAC bit 0 to 1 and test bit 0 to 0, pin RxD0 must be strapped to mode 4. Similarly, RxD1 needs to be set to mode 4 and RxD2 needs to be set to mode 2. Referring to the recommended resistor ratios, you will find the appropriate resistor values to place each strap in the desired mode, and you will find yourself with the strap configuration shown. Again, as a sanity check, you may want to check the voltage on the strap while holding the device in reset to ensure the PHY will be set to the correct mode. LED straps allow some flexibility as well and are offered as 2-level straps, so you only need to worry about pulling the pin high or low. Pulling the pin low configures the strap pin as an active high driver. The LED is on when the strap voltage is high. Conversely, pulling the pin high configures the strap pin as an active low. Also note the difference in diode and current limiting resistor location between the pull-down and pull-up configuration. The parallel pull resistor is required to prevent unknown device states by tying the pin directly to power or ground, as leakage from the pin won't be hard tied through the diode without this parallel resistor. Recall that strap pins have an internal pull. If this internal pull is the same direction as the parallel pull, then the parallel pull is not necessary, though still recommended. Unused LED strap pins can be left floating. Suppose we use the recommended resistor ratios to set a TI PHY to mode 3. How would you determine if the pin will stay within the threshold voltage for mode 3? We can conduct a simple analysis by creating an equivalent circuit accounting for the internal pull of the PHY. Leakage current, temperature, and other factors will be ignored at this time. When the PHY is sampling the potential, the strap resistors and internal pull-down can be simplified as a voltage divider. To verify the resistor configuration will hold the device in the desired mode, we need to determine the maximum and minimum possible potential values to be sampled by the strap. Remember that the real resistance of the resistors may fluctuate based on tolerance. For this example, we'll refer to the internal pull-down resistor as PD and the external resistors as R high and R low. The maximum voltage on the strap, V-strap plus, occurs when R low and PD form the highest equivalent resistance, REQ plus, and R high is at its lowest resistance, R high minus. Based on their tolerances, these values can be calculated as shown. R high minus equals 5.76 times 0.99, which is 5.70. R low plus equals 2.49 times 1.01, and PD plus equals 9 times 1.25. Finding the equivalent circuit and using voltage division, we find that V-strap plus is 0.264 times VDDIO, which is within the range for mode 3 as we expect. The minimum voltage, V-strap minus, occurs when R high is at its highest resistance, R high plus, and R low and PD form the lowest equivalent resistance. R high plus equals 1.01 times 5.76, R low minus equals 0.99 times 2.49, and PD minus equals 0.75 times 9. Again, finding the equivalent circuit and using voltage division, we find that the minimum voltage, V-strap minus, is 0.237 times VDDIO, which is within the range for mode 3. Suppose we deviate from the suggested resistor values and instead use a 2.37K 1% tolerance pull-down resistor. Though the value is close to the recommended 2.49K, after conducting the simple circuit analysis, we find that the minimum strap voltage will leave the device in a floating state between mode 2 and mode 3. Similarly, if we use the recommended strap resistor values but one of them has a 5% tolerance, we find ourselves in a floating mode. Other factors such as temperature, tolerance, and leakage current will additionally affect the potential sampled by the strap pin. To ensure that your straps are set to the correct mode, you may want to carry out a more in-depth analysis. Please review the TI app note linked in this presentation for a detailed analysis of 4-level strap device configuration to ensure you are setting the device to the correct mode. Thank you for watching this video covering bootstraps and TI Ethernet PHYs. Please try our short quiz to check your understanding of this video's content. For additional information about Ethernet PHYs, please view the other Precision Labs videos in the Ethernet series. To find more Ethernet technical resources and search products, visit our website.